In part one of this film, we discussed those chromatographic techniques in which the mobile phase is a gas. In this part, we shall discuss the use of a liquid as the mobile phase. This is liquid chromatography. Its principles are the same as in gas chromatography. The sample components are separated by distribution, either by partition or by adsorption between two phases. The fundamental difference between gas and liquid chromatography is that here a liquid serves as the mobile phase. It is seldom inert and thus competes with the stationary phase for the sample components. It follows that the distribution coefficients of the sample components depend on the nature of the mobile phase, as well as the nature of the stationary phase. A single liquid or a mixture may be used as the mobile phase. Because liquids have higher viscosity than gases, high pressures must be applied when using columns that are long or of small diameter. Proper mobile phase selection depends on the properties of the stationary phase and of the sample. The selection is also based on the rule, like dissolves like, and the solubility of the sample components in the mobile phase depends on their polarity. The matching of polarity is, however, only one aspect in mobile phase selection. The other aspect is related to the stationary phase. In partition chromatography, with a liquid stationary phase distributed over the porous particles of a solid support, the two phases should be non-miscible and insoluble in each other, or almost so. This means that they should be of different polarity, because like would dissolve like. Here again, the partition coefficient determines how the sample components will equilibrate between the two liquids, the mobile and stationary phases. If the sample component is highly soluble in the stationary phase, it will move slowly. If it is more soluble in the mobile phase, it will move more rapidly. If two sample components have identical partition coefficients in a given system, no separation will occur, and another combination of mobile and stationary phases must be tried. In liquid chromatography, a solid adsorbent is most commonly used as the stationary phase. To assure tight packing of the column, vacuum is usually applied to the outlet. Water is normally used to make a slurry for packing the column. The distribution coefficient between the two phases depends on their polarities with respect to the polarities of the sample components. Adsorbents can also be classified as polar or non-polar. Silica gel and alumina are polar, and they adsorb polar samples, such as alcohols and ketones, very well. Charcoal is a non-polar adsorbent and is used primarily for non-polar hydrocarbons. Gradient elution is a mixing technique where the proportion of the components of the mobile phase mixture is changed continuously or in steps, increasing the fraction of the more polar solvent. This serves to displace sample components that are strongly adsorbed by the stationary phase and sharpens the eluted peaks. One design provides a linear increase of the more polar solvent fraction. The other provides an exponential gradient. The systems used in liquid chromatography are similar to those in gas chromatography. A reservoir contains the liquid phase. It is forced through the column by high-pressure gas or by pumping. From the reservoir, the mobile phase moves to the injector port, where the sample is injected by syringe. Separation occurs in the column, and the detector measures the concentration of each component of the sample. Usually, straight glass tubes equipped with filter plugs are used as columns. The larger diameter columns are used commonly and routinely for preparative scale separations. Analytical columns are much smaller in diameter and with lengths from 20 centimeters to 2 meters. Tightly packed, they provide the best resolution, but require high-pressure inlet systems or long retention times. One convenient sampling method uses a sampling valve and loop to inject the sample solution, which in this case is a synthetic dye mixture. As it equilibrates between the mobile phase and the solid adsorbent, the pigments are separated into individual bands. If the same sample were separated on a different stationary phase, a different separation would occur. In some liquid chromatographic systems, the liquid phase flows from a reservoir through a tube into the base of the column and then upward through the column. The separated components may be collected in individual containers for subsequent identification. Detectors commonly used in liquid chromatography are based on the measurement of ultraviolet adsorption or the change in the refractive index of the column effluent. Both types are continuous measurement units and require a mobile phase of uniform composition. Thus, they cannot be used with the gradient dilution technique. Automatic collection of fractions is a common technique in liquid chromatography. The fractions are collected individually for further identification or investigation by additional techniques. Modern liquid chromatographic methods now approach the speed and resolution of chromatography. For example, this 90-second separation of the insecticide EPN was obtained on a 1-meter column 3 millimeters in diameter. The mobile phase was hexane, and the stationary phase 1% oxydipropionitrile on beads having controlled surface porosity. Now let us turn to ion exchange chromatography, a special form of liquid chromatography. Separation occurs because ions of the sample displace the ions of the solid column packing. It is a reversible interchange of ions between the liquid mobile phase and the insoluble porous solid serving as the stationary phase. The solid consists of small beads of a cross-linked polymer that produce a sponge-like network. Distributed throughout it are ionized groups capable of exchanging either cations or anions depending on their compositions. If these groups are highly ionized, we speak of strong exchanges. If the resins are only slightly ionized, we speak of weak exchanges. A typical resin is prepared by the copolymerization of styrene with divinyl benzene. The structure is actually a three-dimensional matrix containing numerous ionizable functional groups. These 4 commercially produced resins represent strong and weak types, both cationic and anionic. Resin behavior depends on the particle size, which affects permeability and rate of exchange, the degree of cross-linking, which affects rigidity, porosity, and swelling, the degree of ionization, which affects the partition coefficient, the nature of the functional group, which determines whether there is cationic or anionic exchange, and the percentages of functional groups in the resin, which affects its capacity. A typical ion exchange process begins with selecting the proper particle size, the degree of cross-linking, and the functional group. The resin is pre-soaked in water to allow swelling and to remove any fine particles. It is then packed wet. When a solution of the sample has been added, water will be pushed continuously through the column. Ion exchange finds major applications in deionization of water and separations of rare earths, alkaline earths, and alkaline metals. One of the most impressive applications of ion exchange chromatography was the separation of more than 50 amino acids in the classical work by Moore and Stein. Temperature and pH were varied in accomplishing this achievement. The last variant of liquid column chromatography is gel chromatography, also called gel permeation or gel filtration chromatography. Here, the stationary phase is a gel consisting of a three-dimensional network of cross-linked polymeric chains. The gels are insoluble in water, but swell greatly in it and have water trapped in each pore. Ideally, the gel works as a filter, screening and separating the sample components by the size of their molecules. The smaller particles penetrate the pores and partition with the solvent inside, and thus are retarded by the gel and therefore elute later. Since large molecules cannot enter the pores, they are not retarded and are eluted rapidly. There are a number of commercially produced gels available in various molecular weight exclusion capabilities. Gel filtration finds applications in desalting of macromolecules and in concentration and fractionation of a wide variety of substances. In the variants of chromatography discussed until now, the stationary phase was packed in a column. It is also possible to carry out the separation on a flat surface that supports the stationary phase. Such techniques are called plane chromatography. Its two main types are thin layer and paper. The basic principles of adsorption, partitioning, and band broadening are also valid in plane chromatography. However, there are no peaks. Instead, there are spots that show the separation. Here, time-lapse photography shows a greatly accelerated separation. The mobile phase is a mixture of alcohols, and the samples are mixtures of ink dyes. They partition between the mobile phase, which is migrating by capillary action, and the stationary phase. In plane chromatography, the so-called retardation factor is used to characterize the individual spots. It is the distance the component moved divided by the distance the mobile phase moved. Naturally, its value is always less than 1. This spot has moved 75% of the distance moved by the mobile phase front, so its RF is 0.75. For this one, RF is 0.40. If the component moves so slowly that the solvent moves off the stationary bed, RF values are calculated relative to an internal standard. TLC plates can be prepared in the laboratory or purchased commercially. They are of many sizes. Even microscope slides can be used as TLC plates. The coating is an adsorbent such as finely divided silica gel, alumina, or cellulose. The thickness of the layer varies between 1/10 and a few millimeters. The plates are usually activated by heating for several hours at about 110 degrees centigrade, then stored in desiccators. The majority of separations are performed on colorless substances and therefore must be made visible after development. Fluorescence, radioactivity, ultraviolet adsorption, or other physical means may be used. The solvent front is marked before the plate is dried. To make the spots visible in this case, the plate is sprayed with ninhydrin, then heat treated. The spots are easily distinguished. The retardation factors are calculated to characterize the spots. Thin layer chromatography is very versatile, fast, and simple. It is a routine procedure in the analysis of drugs and biochemical samples, but cannot be used for trace analysis, and quantitative determinations are difficult. In paper chromatography, water or some other solvent is used in connection with a flat surface of highly purified cellulose paper. The spotted paper is placed in a chamber kept closed to prevent evaporation of the liquids. In some setups, the solvent travels up the paper, known as ascending paper chromatography. In others, it travels down the paper, descending paper chromatography. Like TLC, paper chromatography is rapid, simple, and provides good separating power. But also, trace detections are impossible, and quantitation is difficult and not too accurate. The process is essential in biochemical, pharmaceutical, and clinical laboratories, where small samples of complicated mixtures must be analyzed. In summation, the various liquid chromatographic techniques provide the separation of a wide variety of substances, which, due to their high molecular weight, low volatility, or thermal stability, might not be analyzed by gas chromatography. The chromatographic techniques are complementary to each other. None is the preferred method. Each has a different optimum field of application. By the proper selection of the chromatographic technique, or by a combination of two or more of them, even the most difficult separation can be successfully accomplished.